Okay, so we ended class last time finishing up section 10.3 about phase transitions or phase change. And I had given you, we had sketched together in class what a heating curve looks like, right? And that's what's up on the screen right now. And this is, in fact, the heating curve that we did sketch, which is the heating curve for H2O. And we see on the curve that when it's a single phase and you add heat, the temperature will increase. So you get a sloped line. And when a phase change is occurring, you get a plateau because all the heat energy that's being added is going to breaking IMFs. Or if we're cooling, we're forming IMFs, okay? Only once the phase change is complete and you now are in a new phase, like liquid here, does the temperature begin to increase again. Okay, do you guys remember the two different equations we can use to calculate the amount of heat, Q, that is added if we're heating or if we are cooling, which we'll see an example of that we remove? What are the two equations that you can use? You can use MCAT. When would you use MCAT? When you're in a single phase and you're increasing the temperature or decreasing as the case may be. What is M? Mass in grams. Okay. What is C? You recall that from, that is the specific heat capacity of that substance. You'll be given that information. You'll be given all of this information, okay? It's plug and chug. Now, what we have to recall is that specific heat capacity, the units, are joules per gram times degree C. This is in Celsius. Yesterday, working with the Clausius-Clapeyron equation with gases and vapors, that was Kelvin, right? Heat is Celsius. Just like in Gen Chem 1, they're both at the same time. You just got to know that. So obviously delta T is then the change in temperature in degrees C. What is the other heat equation? Kind of a new one. Nah. Moles, not grams, moles. And delta H is the delta H for that phase change. So if it's melting, that's called heat of fusion, right? If it's vaporization, it's called vaporization. If it's condensation, if it's freezing, we talked a little bit about that yesterday. We're going to see some more times when that is important to know. Am I condensing or am I vaporizing? Am I melting or am I freezing? What am I doing? So on number 9, how much heat, Q, so we're going to calculate Q, is required to evaporate 100 grams of liquid ammonia at its boiling point. The boiling point for liquid ammonia is negative 33.3 degrees C. That's its boiling point. It's negative 33.3 degrees C. What does that mean ammonia is phase-wise at room temp? It's a gas. Yeah, it's a gas. Because its boiling point is negative 33 degrees C. Okay. I'm evaporating 100 grams. Its enthalpy of vaporization is blah, blah, blah. Which equation am I using? I'm using Na. Why? Because I am evaporating, which is a phase change. So I'm going to get the moles of ammonia, and I'm going to multiply it by the delta H. of vaporization, right? Because that's what I'm doing to it. I'm evaporating it. So you'll have to convert 100 grams to moles, right? Using the molar mass of ammonia. Molar mass of ammonia is 17.04. How do you get that? You add it up from the periodic table, right? I just happen to have it memorized, but how do you get that? You add it from the periodic table. And then multiply it by the given vaporization enthalpy, 4.8 kilojoules per mole. You get your answer. You should get 28. Easy. Easy. But I'm going to skip 10 and then come back to it. I'm going to go to 11 now. And what I want you to be thinking about when we are working number 11 is this heating curve. The one that we sketched yesterday for water and the one that's up here on the screen right now in these lecture 2 slides. I want you to be thinking about this curve when we're talking through this question 11. Okay. Calculate how much heat is required to convert 135 grams of ice. That's at negative 15. And actually, if you guys would, on number 11, so on your in class, if you will actually make that say, okay, so 135 grams of ice. Make that say 15.0 for me, please. I meant to put a decimal after that. Okay.
Negative 15.
That's what I meant.
Yeah.
At negative 15.0 to vapor at, and then put 120.0 degrees C. Okay, thank you. And then out to the side here, I give you some data. Right? I give you the melting point. What's the melting point? We already knew this for water, but for any substance, I'm going to give you this information. All right? Okay, delta H of fusion. Remember, that's the enthalpy when the substance is doing what phase change? Fusion is for melting. Doesn't make sense, but that's what it is. Okay. Delta H of vaporization. And then I give you 3 different C values. Do you see what is the difference between those C values? The specific heat capacity depends on what? Yeah, what state is the substance in? If it's solid, it's a different value than if it's liquid. Did y'all see that? Okay. Okay, I'm not going to write all those up here because y'all got them on your sheet. Okay. Think about doing this process. What are you doing? Starting with H2O in what phase? Ice is solid. Okay. Think about your heating curve. Follow along on your heating curve. Look. Y'all watching? Negative 15. I'm actually down here from what's on this graph, but you're on the solid curve, right? You're heating, you're adding heat, you're heating, you're heating. So what is this first Q that you're going to calculate? Step 1 is calculate Q for the solid. Use the MCAT. So step 1, Q equals mass times specific heat capacity of ice, of a solid water, right? Times delta T. What's your delta T? What's your final and what's your initial when you're heating this solid water? -15 is your initial. What's your final? Whatever the melting point of that substance is. For water, it is 0. Final minus initial. Yes, 0 minus -15. T final is your melting point in this scenario. Minus T initial. Y'all do that and tell me what your answer is. You've got your mass. You've got your specific heat capacity of the solid. Joules. And so this answer is going to be calculated. It's going to be joules, right? Multiply all your numbers together. Work it out for yourself. This is what you need to show on your show your work, right? I'm going to show this one, but I'm not going to show each calculation with the numbers filled in. That's for you to do. What do y'all get?
4,200 joules.
4,232.25 is what I got. Yeah. I'm going to tell you guys on these MCAT steps. Just might as well go ahead and convert your answer to kilojoules. Go ahead and convert it to kilojoules. Do this for the MCAT steps. Convert it to kilojoules. So what does that mean? You take your answer, and you divide it by 1,000, right? Whatever this entire answer is, you're going to divide it by 1,000. That'll give you kilojoules every time, right? .23. Yes? Anybody got a question so far? We're good? Okay. Right, Uriam? Yeah? Okay. Okay, so hopefully you can kind of see what we're going to be doing step-wise, moving up the heating curve. Yeah? Next step would be to do what? Calculate the heat added when what is occurring. We've taken our substance to 0 now. What's going to happen next to water? It's gonna melt. It's gonna phase change. You were ahead of us. It's gonna phase change, right? How do you calculate Q during a phase change? Nah. That's second step. What are you gonna do for your third step? I'll put the second step up here, but then we're just talking through it. What's your third step? Heating the liquid water from 0 up to what? It's boiling point, whatever the boiling point is. That's MCAT. Next step, phase change again, but this time it's vaporization. Next step, for this problem, I'm saying take it to 120. So now you have gas. You're heating that gas from 100 degrees up to 120 degrees. That's 6 steps altogether, right? 1, 2, 3, 4, 5. I mean, 5 steps altogether. You got to do each step individually, and then you're going to add them all together. Okay? So I'm going to start writing up here too, but you guys need to be writing this yourself. Do each step. Recognize which value you're going to be using at each step. Okay, step 2. Moles. And then when we're at step 2 in this problem, that's the fusion value, because that's when we're melting, right? We're melting at 0 degrees C. Step 3, Q, mass, times the heat capacity, specific heat capacity when it's a liquid, because that's where we are now. We've taken it to the liquid phase. Above 0, it's liquid. That's where we are. Delta T. Your final temperature for the liquid is whatever its boiling point is. The initial point in this example for the liquid, for this example, we started with the liquid that was at 0, and then we heated it. We kept heating it. So that's, for this example, that was the melting point. You got to use the information in your problem to know your final and initial temperatures. Okay. Step 4, we're phase changing again, only this time we're heating the liquid we're vaporizing the liquid. And then lastly, we're taking that gas we've created now, that vapor, and we're heating it from 100 to 120. All 5 steps. I'm going to give you all a minute to do that. I believe I have these already worked on this slide. Let me see. Okay, I don't have each individual answer step worked out on the slides. I might go back in and add that in tonight. But be these 5 steps, okay? So I'm going to put my answers up here for each step. And you guys, as you're working through it, can compare, or you can take a picture, snapshot of these. Okay, so here I got 45.0. Step 2, okay. You had to add 45.0 kilojoules of heat. Step 3, to take that mass, because it's still 135 grams. It's 135 grams of H2O throughout the whole problem. You didn't lose water. Doesn't say you lost any. It's 135 grams. Step 3, to heat that liquid from its starting point at 0 up to its boiling point, which is 100. I got, and then converting it to kilojoules, I got 56.5 kilojoules to heat the liquid. Okay, then to vaporize that liquid, that 135 grams at 100, once it hits 100 and I'm vaporizing it, I'm phase changing it. Okay, to vaporize that liquid, I got 305 kilojoules. How are y'all getting the moles? What are y'all doing to get the moles? You're doing
135.
135 grams divided by
18.
the molar mass of water, 18.02. Yes, okay, good. And the last step to take that 135 grams of steam to 120 degrees, you have to add 4.97 kilojoules. So what's the total?
I got 415.
415 instead of 416, is that what I have up there?
Yeah.
Ballpark, right?
Yeah.
Total. That's why I said go ahead and change this to kilojoules so that you can add these 5 steps together. And I'm going to want the answer in the answer should be in kilojoules. Okay. The answer will be asked for in kilojoules. So total, adding together, rounding for sig figs. Remember, when we're adding, you go to the last significant decimal place in one of your values. So that means this answer is going to round to the ones place. So again, on my slide, for whenever I did this, I got 416. Kent got 415. What did y'all get? 415? If you got there yet? Ballpark. 416, 415.
I didn't round until my very final answer.
That's probably a difference. Either one of those answers is right. Okay. Total. Now, am I really likely to ask you to do a full 5-step one? No, this was an example. Let's do one where it's not like a full 5 steps and you really got to pay attention to your numbers. So now let's flip back to number 10. Let's try to do this pretty quick. Can you sketch a cooling curve for benzene using that information I gave you? Heating curve goes what way? Up. Well, how do you think a cooling curve goes? Down. Okay. Give it a try. See if you can sketch something before I put it up here on the screen. Look back at the example that we did yesterday with the heating curve and the things that we labeled on that heating curve. You labeled your axes, temperature, heat. You labeled certain temperatures on the side, and you drew sloped lines and then flat lines, and then sloped lines and then flat lines. I don't need you to be like specific about your scaling on a sketch. I'm looking for the important key things. What should this sketch have? Okay. C6H6, benzene. Polar or non-polar, guys?
Non-polar.
Non-polar. Nothing but carbons and hydrogens. What kind of IMFs does it have then?
LDF.
LDF only. Should we expect it to have a very high boiling point then? Not like super high. And it's not super high. Its boiling point is 90.1. Because it is still a fairly large molecule. It's got 6 carbons and 6 hydrogens in it. Cooling curve. What's your y-axis labeled?
Pressure.
No.
Temperature.
Temperature. I think you might be looking back at the.
I was looking at the heating curve, but
that's not a heating curve.
yeah, that makes sense then.
That's not a heating. That picture
Oh,
that
this is the,
that's a phase diagram.
yeah.
That's not a heating curve. Yeah. Okay. Temperature. What's your your x-axis? Okay. So here's the thing. If it's heat, it is heat. But for a cooling curve, is it heat added? Heat removed. You guys, I'm obviously going to have you sketch one of these on the test, yes? Like, obviously, like, that's why I made us do it yesterday and today, obviously, yes? Right, Cynthia? Cynthia's like, I know how your mind works, Miss Poe. I got you. What am I starting my benzene at? Beginning at 100. Okay. What's my first line segment look like? I'm cooling benzene from 100 to what point?
To 0.
So is this?
No, okay.
Okay, what's my first line segment look like?
90.1.
Okay, what can I take it to? I can take it from 100 to this point right here, to the boiling point of the substance. And for benzene, 90.1. Like, I would want you guys to label it this way when you're creating your graph. What special is going to happen here at 90.1? What's going to happen here that's special? Phase change. What is the phase change that's happening here?
So from gas to liquid.
Gas to liquid is called?
It's called condensation.
That's what I want you to label. Then what happens next? I still got to go down to 0. So what happens now on my curve? Okay, so now I have liquid and it's cooling until what temperature? Very good. What's your melting point for the substance? 5.4. So you got to label your melting point on your curve. 5.4 degrees C. And then what is that next line segment going to look like? Flat phase change. What's that phase change called?
Freezing.
Now we're freezing.
So is this a cooling curve?
This would be a cooling curve.
Wait, so then what's a phase diagram?
We haven't talked about those yet.
Okay. So these have been curves the entire time, even though they're like
lines.
Okay.
Yes.
Just making sure.
Okay. I
Yeah.
see a cooling line segment sketch. Yes.
Yeah, sorry, I was hung up on, I haven't gotten through, what is it, 11, the math on 11, so I was just like.
I got you. That's fine. That's fine. A heating curve or a cooling curve is made up of these line segments. What's the last, what am I taking it to now? Down to 0. Okay, so that's where you can make the actual axis be 0. I don't care. I just want you to label these kinds of things. Yes? Okay. What phase is here? Above the boiling point, the phase is a gas. Label that. What phases do you have here when it's condensing? You have 2 at the same time. Now, you can do the little arrows, or you can just put G and L. That's fine with me. I do the arrows because I know it's a equilibrium. They're both there. Middle line segment always represents what phase then? Liquid, always. This phase transition always has which 2 phases in it? Liquid and solid, right? So you can write it just like that. That's fine too. You don't have to do the little double arrow thing. That's okay. Bottom line segment is always the solid. That's what I'm looking for if I ask you to sketch a curve for me on the test. Okay. Now answer a question, because this would also be like what I would do. I would say sketch, and then now answer a question. Right, Cynthia? Calculate Q to take 90 grams, 90.0 grams of benzene, C6H6, at 100 to 25.0 degrees C. How many steps is that? How many individual calculations are you going to have to do? Uh-huh. One calculation? Two calculations? Take it to 25? Three calculations. At 25, it will be a liquid, won't it? Because 25 is in between the melting and the boiling point for that substance. Okay. You don't have to sketch a heating or cooling curve if you're just answering a question like on active chem. I think it's a lovely visual. But you don't have to do that. You just have to recognize that 25 is in between melting and boiling. So it's a liquid. Now, pay attention to what information I gave you in that table on this problem. Yeah, guys. Okay, so this is where I give you in the table delta H of fusion, and I give you delta H of vaporization. Okay. Fusion value was 9.9. The vaporization value was 30.7. Okay. Mm-hmm. So very first step is going to be cool the gas, right? Cool gas from 100 to its boiling point, right, to 90.1. So what equation are you using? If you're cooling, MCAT. If you're cooling, you're changing the temperature, so that's MCAT. We haven't hit the we have not hit the phase change yet, right? What C value are you using? The C value for when it is a gas. And again, go ahead and convert it to kilojoules. Go ahead and divide your answer by 1,000. Yep, that's what I suggest every time. Did y'all figure out where you're going?
No, not yet.
Second step is you are condensing, right? You're doing a phase change. No delta T here. Here's my big question for you guys. Have y'all all done the math for step one? You need a second? I'll give you a second. On this phase change, you are indeed condensing, right? Delta H of condensation, yes? Did I give you delta H of condensation, though? What did I give you that you can use, though? Okay, we know, we talked yesterday, vaporization and condensation are just the reverse processes, right? So what is the delta H of condensation? Excellent. Same value, opposite sign. Right? What would, this is not part of this problem, but just to have in your notes, what would be delta H of freezing if you had to use that?
-9.9.
Excellent, Malachi. Okay, good. So that's how you'll get that. The molar mass of benzene is, again, you'll have to add this up, but it's, yes, 70, thank you, Felipe, 78.12 grams per mole. Yes. Sometimes I'll give you guys the molar mass on the test, just to save time. Why is it what? Why is it that number?
Yeah.
6 times 12.01, right? Plus 6 times 1.01. Okay. What's your third step? Taking it from 90.1 to what temperature? 25. Liquid. Cooling a liquid. Yes, that's what you're doing. Cool the liquid. So Q equals mass times the specific heat capacity for the liquid phase times your delta T, and then convert it to kilojoules. Right? Okay. So let me give you all a minute to get your answers for each part and then add your total up. And we'll see what we got. Yeah. Which one? Which part? Okay, using the MCAT?
Like,
Remember, M is mass, so you're going to use 90 grams. You need moles for step 2, where you're using the NAW equation. Okay, but so if it's 90 grams times the specific heat while it's in the gas phase. If you're starting with it at 100, it's a gas. So that's that number. Gas phase. You see them? Okay. You good?
So you have a question about condensed phase?
Yes.
How do I phase that?
Oh, okay, wait a minute. So right here, you are using the molar mass there.
Yeah.
You should be using the actual number of moles. How do you calculate the number of moles, you guys? Take your grams, 90.0 grams of benzene, and divide it by the molar mass. That divide 90 by 78.12. Okay. That should be, I didn't calculate it separately, but hang on, let me see. That's 1.15 moles of benzene. And so, Hunter, what numbers are we using when it just says M? Whatever mass, the grams that were given, right? Remember, M in the MCAT equation is the mass in grams. N is the number of moles of in that grams.
And then for step 1, it would be 9.9 kilojoules per mole on the MCAT.
Okay. So MCAT, you have your mass, you have your C for the gas, which is the 1.33, right, from the table. Okay, what is your delta T? Not delta H, delta T. What is the change in temperature? If we start with the gas at 100, it goes to 90.1, right? So that, what is that difference? And it needs to be final minus initial. So you're doing 90.1 minus 100. It's a negative answer. Negative, yes? Should be negative 9.9 degrees C.
Just making sure, no, you got it down there.
Okay.
That the delta H is just the negative of what we got.
Yes.
Okay.
Mm-hmm.
If I wrote my answer as like Q removed,
Mm-hmm. Do you still need the negative sign?
should I put the negative?
I think, at least on active chem, it's going to make you put the negative
Right.
sign. So you might as well just put it. If you're just writing like a sentence for me, I'm fine if you say the amount of heat removed is, and then just tell me the value. Yeah, that's fine. That's right.
Yeah.
But I'm pretty sure active chem is going to make you put in the negative sign.
Basically, it's just trying to get to like change. It's just using remove because it's trying to clear you.
Mm-hmm. In fact, in one of my other classes, we actually do absolute value, and we don't use positive or negative sign convention. We say it was removed, or we say it was added, but we just give the absolute
I
value.
actually prefer that.
I'm fine with either way, but I'm pretty sure active chem makes you do the negative sign. No, not yet. Let me do. I was just about to. So step 1, cooling the gas. I got negative 1 point. Looks like I got 0.29. No, 1.19. I got negative 1.19, but it should round to only have 2 sig figs because your delta T. Your delta T is negative 9.9 to the 10th place, so that's 2 sig figs, so this should really be negative 1.2 kilojoules. Really. And this is if you're splitting this up step by step, okay? I'm writing the answer that it would be if that was a single question. I asked for just the total. Like, I would not round at the end of each step. I would round at the end, but again, I'm trying to put it on the board and teach you guys, and so, you know. So you could leave this as negative 1.19, blah, 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 and that's fine. That's fine. Is that what y'all got for the first one? Okay. Second one now. You're doing moles, 1.15 times negative 30.7, right? Negative 35.4 kilojoules, roundabouts. And then the last step, cooling the liquid down to 25, I got negative 10.1 kilojoules, roundabouts. And so your total, when you add it all together, which is the answer I want, the answer I want is the total. This is what I got, negative 46.7 kilojoules is how much heat is removed, right, Kent?
Yeah.
Mm-hmm.
What is the change in temperature for step number 2?
For this one? So you are starting with a liquid that's at 90.1 at the end of the phase change, and you are taking it to 25. So 25 is your final, and 90.1 is your initial. Your delta T should be for this third and final step should be negative 65.1. Okay. Where'd you get that number? You're trying to do delta T, but this is delta H, not delta T. Where do you get delta H from? I'll give it to you in the,
Yeah.
yeah. But remember, Hunter, it's because it's condensation, right? You have to take the vaporization value and use the negative of it, okay?
What did you say about the decimals?
When you are adding numbers, you round your final answer to the same decimal place as the last one, and then all of the numbers you're adding together. The last significant decimal place.
Which is what here?
So in this math, in this multiplication, you have a number that has 3 sig figs, right? 90.0 times a number that also has 3 sig figs, right? 1.33 times a delta T that is negative 9.9, right? That number has 2 sig figs. So this answer, if you were marking decimal places that are significant, that's significant and that's significant. Those 2 digits are significant. 2 sig figs. Same thing on this step. You're multiplying now a number that has 3 sig figs, because this number had 3 sig figs, times a number that has 3 sig figs. So your answer rounds to also have 3 sig figs. So that's this digit, and this digit. Same logic down here. 3 sig figs, 3 sig figs. This delta T also has 3 sig figs, because that's the way the math worked.
Okay. Now, because one of them had 2, when you go to add them all together, do you only do?
No, you now that you are adding numbers, you are going based on decimal place, not number of sig figs. That's a week 1 Gen Chem 1 concept. And we've got to move on, guys. We've already spent way too long on this. Like, this should not have taken this long. So we got to go. Okay. Okay. Next section. Phase diagrams. Okay, what I want y'all to do is look at is that what I want to do? Actually, I guess what I need you to do first is let's just sketch a phase diagram in your notes. Let's do that first. Let's sketch a phase diagram in your notes. So a phase diagram now is not a heating curve. Phase diagram doesn't show the relationship between temperature and heat. Phase diagram shows the relationship between pressure and temperature. So temperature is in degrees C. Pressure can be, I mean, it could be any unit, but in this chapter, a lot of times we're just using the scientific unit, kilopascals. So a phase diagram separates the phases by boundary lines that represent.
Just hurt my head the first time I saw it.
That represent the melting point and the boiling point, right? And we haven't really talked about this because we haven't needed to. And there's also a sublimation point, right? Melting is going from solid to liquid. Boiling is going from liquid to gas. Sublimation is going from what to what?
Solid to gas.
Solid to gas. So here's a phase diagram up on the screen. This is kind of what we're sketching, okay? Section 10.4, all right? This is what I want you to sketch to yourself in your notes. The first boundary line that you draw is always starting at the origin, okay? Starts at the origin, and you come to a point. Doesn't matter, this is just a sketch. It doesn't matter exactly where you stop because you don't have data you're working from, right? That's what we're doing in lab today, is we're gonna make one of these with data. This left side of the graph, where your temperature is low, that's your solid phase. This lower part of your diagram, this is your gas phase. Always on a phase diagram, these are the regions. You have solid on this side, you have gas down here, and you're going to have liquid up here, but I'm not ready to draw that yet. So what does this line represent? What phase change between solid and gas? Sublimation. And if we're going from gas back to liquid, gas back to solid, that's called deposition. So at this pressure, and this temperature, this is how you use it, right? At that pressure and that temperature, that's your sublimation point. That's the temperature where the substance sublimes, right? That's how you use your boundaries. The boundaries give you these melting, boiling sublimation points. They give you the temperatures. But it is dependent on pressure, isn't it? It's dependent on what pressure your system is at. Okay. So here we go. We get here. And then usually you have a line that goes up like that. There's another boundary. I'm going to put a dot here. Y'all put a dot there. Okay. And so now we have our liquid phase. Solid, liquid, gas. This line that separates solid and liquid, what phase change is that?
Melting.
Okay. Melting.
Freezing.
And freezing. If, let's just say, if this was 101.3 kilopascals at this line right here, and I followed this over here to my boundary, and then I followed this down to my temperature line, what would that temperature be called?
The melting point.
The normal melting point. Normal melting point, because that's what it is at 101.3, right?
Mm-hmm.
Third boundary, right here. Did y'all see what I did? Did y'all see me? Draw a line up and out. This boundary separates liquid and gas. Right? So that's vaporization or
Condensation.
excellent condensation. Okay. Again, if I'm at 101.3 and I follow this over here to this boundary, and then I come drop down, what is that temperature called? That's our normal boiling point, right? Going from liquid to gas is boiling point. Yes, good. Okay. Couple of other critical, not to say, I shouldn't have said that word, crucial points on a phase diagram. this point right here, the point where the three boundaries intersect.
Like a triple point.
That is called the triple point. What's special about the triple point? Y'all know, I mean, you can read what it says over there on the screen, but what is the triple point? It's the pressure temperature point where what is happening?
They're all changing phases.
All three phases exist at one time. Normally, we only have two phases coexisting, right? But at the triple point, all three phases exist at the same time. Somewhere in Blackboard, I've got a video, a really cool video of, I think it's carbon dioxide, maybe it's something else. I've got a video of something at the triple point, and you can actually see all three phases at the same time. It's really cool.
Weird.
Yeah, it's super weird, super trippy.
Super creepy.
Triple point. It's the pressure and the temperature where all three phases exist, coexist. And then there's also another point that you need to know about and be able to label on a phase diagram, and that's this data point right here. The point at the end of the liquid gas phase boundary. That is called the critical point. And the critical point is the pressure, it's because all of these are a data point, right? It's pressure and temperature. It's a pressure and a temperature where liquid and gas phase are indistinguishable. You know, liquids have properties, right? Y'all learned some of them, didn't you? Viscosity, surface tension, okay? Gases have properties, don't they? We learned those in Gen Chem 1. Kinetic molecular theory, all that stuff. Above the critical point, at that pressure and temperature or higher, liquids and gases are identically behaved. They behave identically to each other. Indistinguishable. Y'all do not have to write that word, whatever words you want to. You can write whatever synonym you want to. They're identical, they're alike, whatever. That's a lot of syllables in that word.
It's a little brain trippy.
I know, indistinguishable. So we're gonna, I mean, really that's all I wanted you to see. We're gonna do this more in lab today. You can, while we take a little break, look at number 12 on your in-class. You can identify for me the triple point and the critical point. They're kind of already labeled for you on there. Something I'm going to have you do in lab if you want to practice it is if I give you a pressure and a temperature like I'm doing on number 12, can you tell me what phase it's in? Can you find the pressure, temperature, and use the phase to find? So on number 12, I gave you a phase diagram for water. That's the one I'm asking you to use to try to identify. So if you want to practice that while we take a break, and then we're going to come back and finish this chapter. I'm not gonna quiz you guys. So that's what above this, like when we talk about liquid and gas are indistinguishable, that is called a supercritical fluid. The phase that is called above that point is called supercritical fluid, and we're not gonna do much with that. It's fine.
So this, what specifically does this diagram represent? Is it something specific, or is it really?
No, it tells you the melting points, the boiling points, and the sublimation points. Those temperatures at different pressures.
This is just anything?
This is a generic one. It would be for a singular compound. A singular compound. I understand what you're asking now. You create a phase diagram for an individual compound.
Okay.
Yes. So, for example, on this is again just generic. This is not a specific compound. Okay. On number 12 on your in-class, I gave you the phase diagram for water, right? Okay. And if you flip your page over on number 13, I gave you the phase diagram for CO2.
Oh,
Okay. It's different for different compounds. You need to be able to look at a phase diagram and identify what's the normal melting point, what's the normal boiling point. Identify where the triple point is, identify where the critical point is. If I give you a data set, if I give you a pressure and a temperature, can you use a phase diagram and tell me what phase that compound is in? That's what you need to be able to do. So that's practicing with 12 and 13. But like I said, we're going to go ahead and take a break. We'll take maybe 10 minutes. Y'all can work on that, but still have a break. And then we'll come back and we'll finish the chapter. And maybe introduce the next chapter. I don't know yet. We'll see.